The common understanding of gravity is simple. Something falls, gravity pulls it down. You drop a ball, it hits the ground. But the cosmic truth is far stranger. What we think we know about gravity is only the beginning of a mystery that stretches across the entire universe, touching everything from the smallest atom to the largest galaxy. Tonight, we are going to gently explore that mystery together. Before we drift too far into the cosmos, I want to invite you to like this video and subscribe to Cosmic Drift. Your support helps us continue creating these peaceful journeys through space and science. We are about to embark on a slow, calming journey through one of the universe's deepest secrets. Gravity is not what you learned in school. It is not what most people think. And by the end of this exploration, you will see the universe in a completely different way. Let us begin at the beginning, in a quiet orchard, centuries ago. Isaac Newton sat beneath an apple tree. The story says an apple fell and struck him on the head. Whether or not that actually happened does not matter. What matters is what Newton realized in that moment. Objects fall. They always fall toward the earth. But why? Before Newton, people had ideas about why things fell. Some thought heavy objects wanted to return to the ground. Some believed the earth pulled on things with invisible strings. But Newton saw something deeper. He saw a pattern. The same force that pulled the apple down also kept the moon circling the earth. The same force held the planets in their paths around the sun. Newton called this force gravity. He described it with beautiful mathematics. Every object in the universe, he said, attracts every other object. The strength of that attraction depends on two things. First, the mass of the objects. Bigger objects pull harder. Second, the distance between them. The farther apart they are, the weaker the pull. This was the law of universal gravitation. It was elegant, it was simple, and it worked. Newton's equations could predict the motion of planets, the timing of eclipses, the behavior of comets streaking through the solar system. For more than 200 years, scientists used Newton's gravity to understand the cosmos. Everything seemed to fit perfectly into place. But Newton knew something was missing. He could describe how gravity worked, but he could not explain why. What actually caused this attraction between objects? How did the Earth reach out across empty space to pull on the moon? Newton admitted he did not know. He simply described the force. He did not claim to understand its true nature. That mystery lingered for generations. Gravity worked. The math was perfect. But the deeper question remained unanswered. What is gravity really? Then, in the early 1900s, everything changed. Albert Einstein was thinking about light. He was thinking about motion. He was thinking about the nature of space and time themselves. And in that thinking, he found something remarkable. He found that Newton's gravity, as beautiful as it was not the whole story. Einstein realized that space and time are not separate things. They are woven together into a single fabric called spacetime. This fabric is real. It can be bent. It can be stretched. It can be twisted. And massive objects like planets and stars do exactly that. They bend spacetime around them. Imagine spacetime as a rubber sheet stretched flat. Now place a heavy ball on that sheet. The ball sinks down, creating a dip in the surface. If you roll a smaller ball nearby, it will curve toward the heavy ball, not because the heavy ball is pulling on it with some invisible force, but because the sheet itself is curved. The smaller ball is simply following the shape of the surface. This is how gravity works, according to Einstein. The Earth bends space-time around it. The Moon, traveling through that bent space-time, follows a curved path. We call that curved path an orbit, but the Moon is not being pulled. It is simply moving in a straight line through curved space. This was Einstein's theory of general relativity. It was published in 1915, and it changed everything we thought we knew about gravity. General relativity made predictions that Newton's gravity could not. It explained tiny wobbles in the orbit of Mercury that had puzzled scientists for decades. It predicted that light itself would bend when passing near a massive object. In 1919, during a solar eclipse, astronomers observed starlight bending around the Sun, exactly as Einstein had predicted. The universe was listening to Einstein's math. For the first time, humanity had a deeper answer to the mystery of gravity. It was not a force reaching across empty space. It was the shape of space itself. But even Einstein's beautiful theory had limits. There were things in the universe that did not quite fit. And those things would lead us to the most profound misunderstanding of all. In the 1930s, astronomers began studying galaxies beyond our own Milky Way. They measured how fast stars were moving within those galaxies, and they found something strange. Stars on the outer edges of galaxies were moving too fast. According to the visible matter in those galaxies, the stars should have been moving much slower. If they were moving as fast as observed, they should have been flung out into space long ago. But they were not. Something was holding them in. At first, scientists thought there might be more matter in the galaxies than they could see. Maybe there were clouds of cold gas, or dim stars, or planets that were simply too faint to detect. But as they studied more galaxies, the problem only grew. The amount of missing matter was enormous. There was far more matter holding the galaxies together than anyone could account for. Astronomers gave this invisible matter a name. They called it dark matter, and it is one of the deepest mysteries in all of science. Dark matter does not emit light. It does not absorb light. It does not reflect light. It is completely invisible to our telescopes. The only way we know it exists is through its gravitational effects. We can see its gravity pulling on stars, bending light, shaping the structure of entire galaxies. But we cannot see the matter itself. How much dark matter is there? Far more than ordinary matter. The atoms that make up stars, planets, and people account for only about 5% of the universe. Dark matter makes up roughly 27%. That means most of the matter in the universe is something we have never directly detected. Scientists have spent decades searching for dark matter. They have built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with an atom. They have searched for signals in space, looking for clues about what dark matter might be. So far, those searches have found nothing. Some scientists think dark matter is made of particles that interact only through gravity. Others think it might be something even stranger, perhaps particles from dimensions we cannot perceive. There are theories about primordial black holes, tiny black holes formed in the early universe, lurking unseen in the dark. There are ideas about modified gravity, suggestions that perhaps our understanding of gravity itself needs to change. But the truth is, we do not know. Dark matter remains invisible. Its nature remains a mystery. And dark matter is only the beginning. In the late 1990s, astronomers made another discovery, one that was even more shocking. They were studying distant supernova explosions, using them as markers to measure the expansion of the universe. According to General Relativity, the universe should be expanding, but that expansion should be slowing down over time. Gravity, pulling everything back together, should be putting the brakes on, but that is not what they found. they found that the expansion of the universe is not slowing down, it is speeding up. Something is pushing the universe apart. Something is causing galaxies to accelerate away from each other, faster and faster. Astronomers call this mysterious force dark energy. Dark energy is even stranger than dark matter. At least with dark matter, we can see its gravitational effects in specific places, like galaxies and galaxy clusters. But dark energy is everywhere. It fills all of space, and it makes up about 68% of the universe. Think about that for a moment. 68% of the universe is dark energy. 27% is dark matter. Only 5% is the ordinary matter we can see and touch. That means we understand only a tiny fraction of what the universe is made of. What is dark energy? Scientists do not know. Some think it is a property of space itself, a kind of energy that exists even in a vacuum. Einstein's equations actually allow for this. He called it the cosmological constant. But if space itself has energy, why does it have that particular amount? Why is the universe expanding at the rate it is, and not faster or slower? Other scientists think dark energy might be a new kind of field, something like the fields that govern other forces in nature. Or perhaps it is a sign that general relativity breaks down on the larger scales. Maybe gravity behaves differently across billions of light years than it does in our solar system. Once again, we are faced with a deep mystery. We can measure dark energy's effects. We can see it pushing the universe apart, but we do not understand what it is or why it exists. And so, when we talk about gravity, we are not just talking about apples falling from trees. We are talking about an invisible scaffold that holds galaxies together, a mysterious force accelerating the expansion of the cosmos, and a fabric of space-time that bends and warps in ways we are only beginning to understand. This is the misunderstanding. We think gravity is simple. We think we know what it is, but the universe is showing us again and again that there is so much more to discover. Now let us turn our attention to the most extreme places in the universe, places where gravity becomes so powerful that it warps reality itself. Black holes are the ultimate expression of gravity. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. To understand black holes, we need to think about what happens when matter is compressed into a smaller and smaller space. Imagine taking the Earth and squeezing it down. First, you compress it to the size of a basketball, then to the size of a marble, then to the size of a grain of sand. As you compress it, the gravity at the surface becomes stronger and stronger. Eventually, if you compress it enough, something extraordinary happens. The gravity becomes so strong that the escape velocity, the speed needed to break free, exceeds the speed of light. At that point, you have created a black hole. The boundary around a black hole is called the event horizon. Once something crosses the event horizon, it can never come back. Light itself cannot escape. That is why black holes are black. But the event horizon is not a physical surface. It is simply the point of no return. If you were falling toward a black hole, you would not feel anything special as you crossed the event horizon. You would just keep falling. But to someone watching from far away, something strange would happen. As you approach the event horizon, you would appear to slow down. Time itself would seem to stretch. You would never quite reach the horizon, at least not from the outside observer's perspective. You would appear frozen in time, slowly fading from view. This is one of the strangest predictions of general relativity. Time does not flow at the same rate everywhere. Near a massive object, time slows down. The stronger the gravity, the slower time moves. Near the event horizon of a black hole, time slows to a crawl. Inside the event horizon, things become even stranger. At the very center of a black hole, General Relativity predicts something called a singularity. This is a point where density becomes infinite, where space-time itself is torn apart. Our equations break down. We cannot describe what happens there. The singularity is a place where physics, as we know it, stops working. Do singularities really exist? We do not know. Some scientists think that quantum mechanics, the physics of the very small, might prevent singularities from forming. Others think the singularity is real, but we simply do not have the right theory to describe it yet. Black holes are not just theoretical. We have observed them. We have seen stars orbiting invisible companions, moving so fast that the companion must be incredibly massive and incredibly small. A black hole. We have detected gravitational waves, ripples in space-time, created when two black holes spiral together and merge. We have even taken a picture of a black hole. In 2019, astronomers released an image of the supermassive black hole at the center of the galaxy Messier 87. The image showed a glowing ring of light surrounding a dark shadow, the event horizon itself. These observations confirm that black holes exist. They are real, and they are everywhere. At the center of almost every large galaxy, including our own Milky Way, there is a supermassive black hole, millions or even billions of times more massive than the Sun. Gravity in these extreme places is not a gentle pull. It is a cosmic whirlpool, dragging space-time itself into an abyss. But gravity does more than just trap light. It also bends light. Imagine a beam of light traveling through space. If that light passes near a massive object, like a star or a galaxy, the space-time around that object is curved. The light follows that curve. To us, watching from a distance, it looks like the light has bent. This is called gravitational lensing, and it is one of the most beautiful effects of general relativity. Astronomers use gravitational lensing to study distant objects. When light from a faraway galaxy passes near a massive galaxy cluster, the gravity of the cluster bends the light. This can create multiple images of the distant galaxy, or stretch it into arcs and rings. By studying these distortions, astronomers can learn about both the distant galaxy and the mass of the cluster bending the light. Gravitational lensing has also revealed dark matter. When astronomers study how light is bent by galaxy clusters, they find that the clusters have far more mass than the visible matter can account for. The invisible mass, the dark matter, is doing most of the bending. In a sense, gravity is a lens through which we see the universe. It shapes the paths of light, revealing things we could never see otherwise. And gravity does something else, something even more profound. It creates waves. When massive objects accelerate, they disturb space-time. That disturbance spreads outward at the speed of light, like ripples on a pond. These are gravitational waves. Einstein predicted gravitational waves in 1916, just a year after he published General Relativity. But he thought they would be far too weak to detect. It took 100 years to prove him right. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time. The waves came from two black holes, each about 30 times more massive than the Sun, spiraling together and merging into a single larger black hole. The collision released more energy in a fraction of a second than all the stars in the visible universe combined, and that energy rippled through space-time, traveling across 1 billion light years, eventually reaching Earth and causing the mirrors in LIGO's detectors to move by less than the width of a proton. Since that first detection, LIGO and other detectors have observed dozens of gravitational wave events, black hole mergers, neutron star collisions. Each detection is a new way of listening to the universe. We are no longer just watching the cosmos with telescopes. We are hearing it, feeling the vibrations of space-time itself. Gravitational waves are opening a new window on the universe. They let us observe events that emit no light, events hidden from our telescopes. They let us test general relativity in the most extreme conditions. And they remind us that space-time is not a static stage. It is alive, dynamic, rippling and bending with the motion of matter and energy. Gravity, then, is not just a force. It is the choreography of the cosmos, the rhythm that moves everything from falling apples to colliding black holes. But there is still a problem. There is still something missing. General relativity describes gravity beautifully on large scales. Planets, stars, galaxies, the expansion of the universe. But when we try to apply general relativity to the very small, to the quantum world, everything falls apart. Quantum mechanics is the physics of atoms and particles. It is a strange and wonderful theory, describing a world where particles can be in multiple places at once, where the act of observing changes what you observe, where uncertainty is woven into the fabric of reality. Quantum mechanics works. It has been tested countless times. It explains the behavior of electrons, the structure of atoms, the properties of light. It is one of the most successful theories in all of science. But quantum mechanics and general relativity do not fit together. They are based on fundamentally different ideas. Quantum mechanics describes a world of probabilities and uncertainties. General relativity describes a smooth, continuous fabric of space-time. When physicists try to combine them, the math breaks down. This is the problem of quantum gravity. How do we describe gravity in the quantum world? What happens to space-time at the smallest scales, scales far tinier than an atom, where quantum effects should dominate? We do not have any answer. We do not have a theory of quantum gravity, but scientists have ideas. One idea is the graviton. If gravity is truly a force, like the electromagnetic force or the nuclear forces, then it should be carried by a particle. Photons carry the electromagnetic force. Gluons carry the strong nuclear force. Maybe gravity is carried by a particle called the graviton. If gravitons exist, they would be incredibly difficult to detect. Gravity is by far the weakest of the fundamental forces. A single graviton would interact so weakly with matter that we might never be able to observe one directly. But the idea is elegant. It fits with the quantum description of other forces. And so, physicists continue to search for signs of gravitons, even though the search is extraordinarily challenging. Another idea is string theory. String theory proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. Different vibrations of these strings correspond to different particles. One vibration might be an electron, another might be a photon, and one particular vibration would be a graviton. String theory is mathematically beautiful. It naturally includes gravity. It unites all the forces of nature into a single framework. But it comes with a cost. String theory requires extra dimensions. Not just the 3 dimensions of space and 1 dimension of time that we experience, but as many as 10 or 11 dimensions in total. Where are these extra dimensions? String theorists suggest they are curled up, hidden at scales so small we cannot detect them. String theory has not been proven. It makes few testable predictions. But it remains one of the most promising approaches to quantum gravity. There is also loop quantum gravity. This theory tries to combine general relativity and quantum mechanics more directly. It suggests that space-time itself is not smooth and continuous, but made of discrete units, tiny loops of space woven together like a fabric. At large scales, space-time looks smooth, just as a piece of cloth looks smooth from a distance. But zoom in close enough, and you would see the individual threads. Loop quantum gravity has intriguing implications. It suggests that singularities, like the one at the center of a black hole, might not be infinitely dense points. Instead, they might be regions of extremely high but finite density. The theory might eliminate singularities altogether, but loop quantum gravity also has challenges. It is difficult to make predictions that can be tested, and it does not yet unify gravity with the other forces of nature the way string theory does. There are other ideas too. Some scientists think gravity might emerge from deeper, more fundamental principles. Others are exploring the idea that space-time itself might be an illusion, a kind of hologram projected from a lower dimensional reality. These are wild ideas, speculative and unproven, but they show how far scientists are willing to go to solve the mystery of gravity. The search for a theory of quantum gravity is one of the great quests of modern physics. It is a quest to understand the universe at its most fundamental level, to find the rules that govern reality when gravity and quantum mechanics both matter. In the heart of a black hole, or in the first moments after the Big Bang, we do not have the answer yet, but we are looking. And in that search, we are uncovering new questions, new mysteries, new ways of thinking about the universe. So where does this leave us? What have we learned about gravity? We have learned that gravity is not a simple force. It is the curvature of space-time. It is the shape of the universe itself. We have learned that most of the universe is invisible. Dark matter holds galaxies together. Dark energy pushes the universe apart. We can see their effects, but we do not know what they are. We have learned that gravity can be extreme. Black holes bend space-time so severely that nothing can escape. Gravitational waves ripple through the cosmos, carrying news of violent collisions across billions of light years. We have learned that gravity and quantum mechanics do not yet fit together. We do not have a complete theory of reality. The universe is still teaching us, and perhaps most importantly, we have learned that gravity is deeply mysterious. For all our progress, for all our beautiful equations, there is still so much we do not understand. Why is gravity so weak compared to the other forces? The electromagnetic force, for example, is many orders of magnitude stronger than gravity. Two electrons repel each other with far more force than they attract each other through gravity. Why is gravity so feeble? Some physicists think gravity might be weak because it leaks into extra dimensions. If string theory is correct, and there are hidden dimensions we cannot see, then gravity might be spreading out into those dimensions, diluting its strength in our familiar three-dimensional space. This is speculative, but it is a fascinating idea. Another mystery is the cosmological constant problem. If space itself has energy, if dark energy is real, then our equations predict that the amount of dark energy should be enormous, far greater than what we observe. In fact, the predicted value is so large that the universe should have torn itself apart long ago. But it did not. The actual amount of dark energy is tiny compared to what the equations suggest. Why? No one knows. There is also the mystery of the Big Bang. General Relativity tells us that the universe began in a state of infinite density, a singularity from which space and time themselves emerged. But what caused the Big Bang? What, if anything, existed before it? And how did the universe go from that singular point to the vast expanse we see today? These questions touch on the very origin of existence, and we do not have answers. Even the nature of spacetime itself is not fully understood. Is spacetime fundamental? Or is it made of something deeper? Does it have a smallest unit, a quantum of space and time? If so, what are the properties of that quantum? These are questions that a theory of quantum gravity might answer. But until we have that theory, space-time remains a beautiful mystery. And so, we return to where we started. Gravity is the force we think we understand. But the more we learn, the more we realize how much we do not know. This is not a failure. This is the nature of science. Every answer leads to new questions. Every discovery opens new frontiers. The universe is vast and complex, and our understanding is always growing. It is easy to feel small in the face of such mysteries. We are tiny beings on a small planet, orbiting an ordinary star, in an unremarkable corner of the galaxy. And yet, we have the capacity to ask these questions. We have the ability to look up at the night sky and wonder. We have built telescopes and detectors, written equations and theories, all in an effort to understand the cosmos. And we are part of this universe. The atoms in our bodies were forged in the hearts of stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was created in stellar furnaces and scattered into space when those stars died. We are made of stardust. We are the universe becoming aware of itself. Gravity connects us all. It binds the Earth to the Sun to the galaxy to the cosmic web of structure that spans the universe. It is the invisible thread that ties everything together. And in studying gravity, we are studying the very fabric of existence. So as you drift off tonight, remember this: you are not separate from the universe. You are a part of it. The same laws that govern the motion of galaxies govern the beating of your heart. The same space-time that bends around a black hole curves gently around you. You are woven into the cosmic dance. Gravity is the force we misunderstand, but it is also the force that holds everything together. It is the rhythm of the cosmos, the shape of reality, the silent music that plays in the background of existence. And as we continue to explore, to question, to seek answers, we are not just learning about the universe. We are learning about ourselves. We are discovering our place in the grand story of space and time. The mystery of gravity is far from solved. Dark matter and dark energy remain hidden. Quantum gravity eludes us. Black holes guard their secrets. But that is what makes the journey so compelling. That is what makes the search so beautiful. We do not need to have all the answers to appreciate the wonder. We do not need to understand everything to feel the connection. The universe is here, vast and mysterious, and we are part of it. So rest easy. Let the questions linger. Let the mysteries remain. Tomorrow, the search will continue. New telescopes will peer deeper into space. New detectors will listen for gravitational waves. New theories will be proposed and tested. And slowly, piece by piece, we will uncover more of the truth. But tonight, just be. Be a part of the universe. Be a part of the gravitational dance. Feel the pull of the Earth beneath you, the curve of space-time around you, the invisible threads connecting you to everything that is. Gravity is the force we misunderstand, but it is also the force that makes us who we are. It is the heartbeat of the cosmos, the structure of reality, the foundation upon which everything rests. And in the end, that is enough. We do not need to understand every detail to appreciate the beauty. We do not need to solve every mystery to feel the wonder. The universe is here. We are here. And gravity, in all its strange and subtle glory, holds us together. Sleep well. Dream of stars and galaxies, of black holes and ripples in spacetime, of the vast cosmic dance that plays out across billions of light years. And know that you are part of that dance. You are a note in the symphony. You are a thread in the fabric. You are made of stardust, held together by gravity, floating through a universe that is far more mysterious and far more beautiful than we ever imagined. But before we close our eyes completely, let us explore a little further. There are so many more layers to this gravitational mystery, so many more ways that gravity shapes our existence and our understanding of reality. Let us talk about time. We mentioned earlier that time flows differently near massive objects. But what does that really mean? How does gravity affect time in ways we can feel and measure? Imagine two identical clocks. You place one on the ground and carry the other to the top of a tall mountain. You leave them running for a day, then compare them. The clock on the mountain will be slightly ahead of the clock on the ground. Time moves faster at higher altitudes. The difference is tiny, just a few nanoseconds over a day. But it is real, and it is measurable. In fact, the Global Positioning System, GPS, has to account for this effect. GPS satellites orbit high above the Earth, where time runs faster than it does on the surface. If the system did not correct for this time difference, GPS coordinates would drift by several kilometers per day. Your phone's map would be useless. This is gravitational time dilation. The stronger the gravity, the slower time flows. On the surface of the Earth, gravity is relatively weak, so the effect is small. But near a black hole, the effect is enormous. Imagine you had a friend who could survive near a black hole's event horizon. You watch from a safe distance as they hover just outside the horizon. To you, time for your friend appears to slow down dramatically. They move in slow motion. Their words are drawn out. Their clock ticks slower and slower. If they stayed there for what seems like an hour to them, years or even decades might pass for you. This is not an illusion. Time really is moving at different rates. If your friend returned to you after their hour near the black hole, they would find that you had aged far more than they had. Time, in a sense, is flexible. It bends and stretches with gravity. This has profound implications. It means that when we talk about the age of the universe, we have to be careful. Age is relative. Different parts of the universe, with different gravitational fields, experience time differently. The universe does not have a single universal clock. It also means that time travel, in a sense, is possible. If you could travel to a region of strong gravity, spend some time there, and return, you would have traveled into the future. You would find that more time had passed for everyone else than had passed for you. You cannot go back in time, but you can, in principle, move forward faster than others. Of course, actually doing this is extraordinarily difficult. Getting close to a black hole without being torn apart is nearly impossible, and the energy required to escape from such a strong gravitational field is immense. But the physics allows it. Gravity gives us a window, however narrow, into the strange nature of time itself. Now, let us think about gravity in our daily lives. We often take it for granted. We wake up, we walk, we move through the world, all without thinking about the force holding us to the ground. But gravity is always there, silently shaping our existence. Gravity determines how our bodies function. Our muscles, our bones, our cardiovascular system, all evolved in Earth's gravitational field. When astronauts spend months in space, where gravity is nearly absent, their bodies change. Bones lose density. Muscles weaken. The heart does not have to work as hard to pump blood, and it becomes less efficient. Astronauts returning from long stays on the International Space Station often need weeks or months to readjust to Earth's gravity. Gravity also affects how we perceive the world. Our sense of balance relies on tiny structures in our inner ears that detect the pull of gravity. When those structures are disrupted, we feel dizzy and disoriented. Gravity is part of how we know which way is up and which way is down. Even our sense of weight is a consequence of gravity. When you stand on a scale, the number you see is a measure of the force of gravity pulling on your mass. On the moon, where gravity is weaker, you would weigh only about 1/6 of what you weigh on Earth. Your mass would be the same, but the gravitational pull would be less. Gravity shapes the Earth itself. The planet is round because gravity pulls all the matter toward the center. Mountains rise only so high before the weight of the rock causes them to collapse. The tallest mountain on Earth, Mount Everest, is near the limit of how high a mountain can be on a planet with Earth's gravity and composition. On Mars, where gravity is weaker, mountains can be taller. Olympus Mons, the tallest volcano in the solar system, rises about 22 kilometers above the surrounding plains, more than twice the height of Everest. The weaker gravity allows the mountain to support its own weight. Gravity also drives geological activity. The heat inside the Earth, which powers volcanoes and plate tectonics, comes partly from the decay of radioactive elements, but it also comes from the gravitational energy of the planet's formation. When the Earth formed, countless small bodies collided and merged. Each collision released energy, heating the planet. That heat is still slowly escaping, driving the movement of continents and the eruption of volcanoes. Tidal forces are another manifestation of gravity. The moon pulls on the Earth, but it pulls more strongly on the side of the Earth closest to it. This creates a bulge in the oceans on the side facing the moon. There is also a bulge on the opposite side, because the moon pulls less strongly there, and the water is left behind. As the Earth rotates, these bulges move around the planet, creating the tides. The sun also creates tides, though they are smaller than the moon's tides. When the sun and moon align during a new moon or full moon, their tidal forces add together, creating especially high tides called spring tides. When the sun and moon are at right angles during the first and third quarters of the moon, their tidal forces partially cancel out, creating lower tides called neap tides. Tidal forces can be incredibly powerful. Near a black hole, the difference in gravitational pull from one side of an object to the other can be so great that the object is stretched and torn apart. This process is called spaghettification. If you fell into a black hole feet first, the gravity pulling on your feet would be much stronger than the gravity pulling on your head. You would be stretched into a long, thin strand. It is not a pleasant thought, but it is a vivid illustration of how extreme gravity can be. Tidal forces also play a role in the evolution of planetary systems. The moon is slowly moving away from the Earth because of tidal interactions. As the Earth's rotation drags the tidal bulges ahead of the moon, those bulges pull on the moon, transferring energy and causing it to spiral outward. The process is slow, only a few centimeters per year, but over billions of years, it has moved the moon significantly farther from Earth than it was when it first formed. Eventually, billions of years from now, the moon will move far enough away that the Earth's rotation and the moon's orbit will be locked together. The Earth will always show the same face to the moon, just as the moon already always shows the same face to the Earth. At that point, the tidal interactions will have reached an equilibrium. Tidal forces can also heat moons and planets. Jupiter's moon Io is the most volcanically active body in the solar system. Its volcanism is powered not by radioactive decay, but by tidal heating. Jupiter's immense gravity constantly squeezes and stretches Io as it orbits, generating friction and heat inside the moon. The result is a world covered in erupting volcanoes and lava flows. Europa, another moon of Jupiter, is also heated by tides. Beneath its icy surface, Europa is thought to have a vast ocean of liquid water kept warm by tidal heating. That ocean might be one of the best places in the solar system to search for extraterrestrial life. Gravity, in this case, creates the conditions for life to exist far from the Sun. Gravity also plays a role in the formation of planetary systems. Stars form from clouds of gas and dust that collapse under their own gravity. As the cloud collapses, it begins to spin faster, just as a figure skater spins faster when they pull in their arms. The spinning cloud flattens into a disk, with the forming star at the center. In the disk around the young star, particles of dust stick together, growing into larger and larger clumps. These clumps collide and merge, forming planetesimals, then protoplanets, and eventually full-size planets. Gravity is the force that drives this process, pulling matter together, building worlds from dust. The arrangement of planets in a solar system is also influenced by gravity. Planets can migrate inward or outward as they interact gravitationally with the disk of gas and dust, or with other planets. Some exoplanets, planets orbiting other stars, are found in surprising locations. Hot Jupiters, for example, are massive planets orbiting very close to their stars, far closer than any planet in our solar system. These planets likely formed farther out and then migrated inward, driven by gravitational interactions. Gravity even affects the light we see from distant stars. When a planet passes in front of its star, it blocks a tiny fraction of the star's light. This is called a transit. By measuring the dimming of the star's light, astronomers can detect the planet and learn about its size and orbit. But gravity also causes a more subtle effect. As the planet moves, its gravity tugs on the star, causing the star to wobble slightly. This wobble shifts the star's light toward the blue when the star is moving toward us, and toward the red when it is moving away. By measuring these shifts, astronomers can determine the planet's mass. This technique, called the radial velocity method, was one of the first used to detect exoplanets. It has revealed hundreds of worlds orbiting other stars, many of them unlike anything in our solar system. And it is all thanks to gravity, the invisible force that pulls stars and planets together. Let us now think about the largest structures in the universe. Galaxies are not scattered randomly through space. They are organized into clusters, and those clusters are organized into superclusters, forming a vast cosmic web. What creates this structure? Gravity. In the early universe, just after the Big Bang, matter was distributed almost uniformly. But there were tiny variations, tiny regions where the density was slightly higher or slightly lower. In the denser regions, gravity pulled in more matter. As more matter accumulated, the gravitational pull grew stronger, attracting even more matter. Over billions of years, these small variations grew into the massive structures we see today. Dark matter played a crucial role in this process. Because dark matter does not interact with light, it could collapse under gravity without being pushed apart by radiation. Dark matter formed the scaffolding, the framework, upon which galaxies and galaxy clusters formed. Ordinary matter, the atoms and molecules that make up stars and planets, fell into the gravitational wells created by dark matter. The result is a universe that looks like a cosmic web. Long filaments of galaxies stretch across hundreds of millions of light years, connected by nodes where galaxy clusters reside. In between the filaments are vast voids, regions with very few galaxies. This structure is a direct result of gravity acting over cosmic time. And the cosmic web is still evolving. Galaxies are still moving, still merging, still forming new stars. Gravity continues to shape the universe on the grandest scales. But gravity is not the only force at play on large scales. Dark energy is pushing the universe apart, counteracting the attractive pull of gravity. In the distant future, as dark energy continues to dominate, the cosmic web will be torn apart. Galaxy clusters will become isolated islands in an ever-expanding sea of space. Eventually, even galaxies themselves might be torn apart if the expansion accelerates enough. This possible fate of the universe is called the Big Rip. It is one of several scenarios for how the universe might end. Another is the Big Freeze, where the universe continues expanding forever, gradually cooling and fading into darkness. A third is the Big Crunch, where gravity eventually overcomes dark energy, causing the universe to collapse back into a single point. Which fate awaits us depends on the properties of dark energy and gravity on the largest scales, and those properties are still being studied. The future of the universe is an open question, but let us return to the present, to the here and now, where gravity continues to work its quiet magic. Consider the solar system. The sun holds the planets in their orbits, but the planets also pull on each other. These gravitational interactions create a delicate balance, a celestial dance that has continued for billions of years. Jupiter, the largest planet, has a particularly strong influence. Its gravity has shaped the solar system in many ways. It has cleared its orbit of smaller bodies, flinging them into the outer solar system or out of the solar system entirely. It has captured families of asteroids called Trojans that orbit the Sun at the same distance as Jupiter, locked in gravitationally stable positions, and it has protected the inner solar system from comets. Many comets that would have collided with Earth have been deflected or captured by Jupiter's gravity. The asteroid belt between Mars and Jupiter is also a result of gravity. In the early solar system, there was enough material in that region to form a planet, but Jupiter's gravity stirred up the asteroids, increasing their speeds and preventing them from sticking together. Instead of a planet, we have a belt of rocky debris. Even the moons of the planets are shaped by gravity. Most large moons are tidally locked, always showing the same face to their planet, just as our moon does to Earth. This happens because gravity creates a tidal bulge on the moon. Over time, friction slows the moon's rotation until the bulge is always aligned with the planet. Some moons have even stranger fates. Phobos, one of Mars's two small moons, is slowly spiraling inward. In about 50 million years, it will either crash into Mars or be torn apart by tidal forces, forming a ring around the planet. Gravity giveth, and gravity taketh away. Rings themselves are a gravitational phenomenon. Saturn's magnificent rings are made of countless particles of ice and rock, all orbiting the planet. The particles are held in place by a balance of gravitational forces. Saturn's gravity pulls them inward. Their orbital motion creates an outward centrifugal effect, and the gravitational influence of Saturn's moons creates gaps and waves in the rings, sculpting them into the intricate patterns we see. Rings are fragile. The particles in a ring are constantly colliding, and those collisions can send particles into new orbits. Over time, rings spread out and eventually dissipate. Saturn's rings might be relatively young, perhaps only a few 100 million years old. They might be the remnants of a moon that was torn apart by tidal forces, or the debris from a collision. Gravity created them, and gravity will eventually destroy them. Gravity also governs the lives of stars. A star is born when a cloud of gas collapses under its own gravity. As the cloud contracts, it heats up. Eventually, the core becomes hot enough and dense enough for nuclear fusion to begin. Hydrogen atoms fuse into helium, releasing energy. That energy creates an outward pressure that balances the inward pull of gravity. The star reaches equilibrium, shining steadily for millions or billions of years. The more massive a star, the stronger its gravity and the hotter and denser its core. Massive stars burn through their fuel quickly, living only a few million years. Less massive stars, like the Sun, burn their fuel more slowly and can shine for billions of years. The smallest stars, red dwarfs, burn so slowly that they can shine for trillions of years, far longer than the current age of the universe. When a star runs out of fuel, gravity takes over again. For stars like the Sun, the core collapses until the electrons in the atoms are packed so tightly that quantum mechanics prevents further collapse. The result is a white dwarf, a dense, hot remnant about the size of the Earth. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. For more massive stars, gravity can overcome even the electron pressure. The core collapses further, crushing the electrons and protons together to form neutrons. The result is a neutron star, even denser than a white dwarf. A neutron star might be only 20 kilometers across, but it contains more mass than the Sun. A teaspoon of neutron star material would weigh billions of tons. Neutron stars are fascinating objects. They spin rapidly, sometimes hundreds of times per second, and they have incredibly strong magnetic fields. Some neutron stars emit beams of radiation from their magnetic poles. As the star spins, those beams sweep across space like a lighthouse. If the beam points toward Earth, we see regular pulses of radiation. These objects are called pulsars. Pulsars are so regular that they can be used as cosmic clocks. Some pulsars are accurate to within a few millionths of a second over many years. Astronomers have even proposed using pulsars as navigational beacons for spacecraft traveling through the solar system. For the most massive stars, even neutron star pressure is not enough to resist gravity. The core collapses completely, forming a black hole. And we are back to the most extreme manifestation of gravity, the point where space-time itself is torn apart. But black holes are not just endpoints. They are also engines. Supermassive black holes at the centers of galaxies can power some of the brightest objects in the universe. As matter falls toward a black hole, it forms a swirling disk called an accretion disk. Friction in the disk heats the matter to millions of degrees, causing it to emit intense radiation. Some of this energy is channeled into jets that shoot out from the poles of the black hole at nearly the speed of light, extending for thousands of light years. These jets can affect entire galaxies. They can heat the gas in the galaxy, preventing it from cooling and forming new stars. They can trigger bursts of star formation in nearby regions. They can even blow gas out of the galaxy entirely. Supermassive black holes, through their gravitational influence and the energy they release, help regulate the evolution of galaxies. Gravity, then, is not just a passive force. It is active, dynamic, creative. It builds stars and planets. It shapes galaxies. It powers the most energetic events in the universe. It is the sculptor of the cosmos. And yet, for all its power, gravity remains mysterious. We still do not understand its quantum nature. We still do not know what dark matter and dark energy are. We still cannot predict exactly how galaxies form and evolve. There is so much left to learn, but that is the beauty of science. Every answer raises new questions. Every discovery opens new paths of inquiry. And gravity, in its quiet, persistent way, continues to guide us forward. Now let us consider another aspect of gravity, one that touches on philosophy as much as physics. Gravity is universal. It affects everything, everywhere, at all times. There is no escaping it. Even light, which has no mass, is affected by gravity because light travels through space-time, and space-time is curved by mass. This universality makes gravity special. The electromagnetic force affects only charged particles. The strong nuclear force acts only on quarks and gluons. The weak nuclear force is responsible for certain types of radioactive decay. But gravity affects everything. It is the only force that truly touches all matter and energy in the universe. This raises a deep question. Why is gravity so different from the other forces? Why does it act on everything, while other forces are more selective? And why is it so much weaker? These questions hint at something profound. Perhaps gravity is not a force in the same sense as the others. Perhaps it is a more fundamental aspect of reality, the geometry of space-time itself. The other forces might be properties of fields that exist within space-time. But gravity is space-time. If that is true, then understanding gravity means understanding the very fabric of existence. It means understanding not just how things move, but why space and time exist at all. This is where physics meets philosophy. What is space? What is time? Are they real? Or are they just convenient ways of describing relationships between objects? If space-time is curved by mass, does that mean space and time are physical things that can be bent? Or are they abstract concepts, mathematical tools we use to make sense of the world? These are not easy questions. Philosophers have debated them for centuries, and physicists are still grappling with them today. Some theories suggest that space and time might emerge from something more fundamental. In certain approaches to quantum gravity, space-time is not the starting point. Instead, space-time is built up from simpler, more basic entities. This would mean that space and time, as we experience them, are not truly fundamental. They are emergent properties, like temperature or pressure, which emerge from the motion of countless atoms. If space-time is emergent, then gravity is also emergent. It is not a fundamental force, but a collective behavior of whatever the universe is really made of. This is a radical idea. It challenges our most basic assumptions about reality. But it is an idea that some physicists take seriously. There is also the question of what lies beyond space-time. If the universe began with a Big Bang, what was there before the Big Bang? Some physicists argue that the question is meaningless because time itself began at the Big Bang. There is no before because time did not exist. Others propose that the Big Bang was not a true beginning, but a transition from some previous state. Perhaps the universe is cyclic, expanding and contracting over and over. Or perhaps our universe is just one of many, part of a larger multiverse. These ideas are speculative. They are difficult, perhaps impossible to test, but they show the depths of the mystery. Gravity, in leading us to questions about space-time and the origin of the universe, leads us to the edge of what we can know. And yet, even as we explore these deep questions, gravity continues to work in practical, everyday ways. Engineers use our understanding of gravity to design buildings and bridges. Aerospace engineers use it to launch satellites and plan missions to other planets. doctors study how microgravity affects the human body, preparing for long-duration space travel. Gravity is both a cosmic mystery and a practical tool. It is a subject of profound theoretical inquiry and a force we harness every day. Let us think about spaceflight for a moment. Launching a rocket into space is all about overcoming gravity. The rocket must reach a speed fast enough that it can escape the Earth's gravitational pull. This speed, called escape velocity, is about 11 kilometers per second at the Earth's surface. Once in space, spacecraft use gravity in clever ways. The gravity assist, or slingshot maneuver, is a technique where a spacecraft flies close to a planet, using the planet's gravity to change its speed and direction. As the spacecraft swings around the planet, it can gain speed, stealing a tiny bit of the planet's orbital energy. This allows spacecraft to reach distant destinations without carrying enormous amounts of fuel. The Voyager spacecraft, launched in the 1970s, used gravity assists from Jupiter and Saturn to reach the outer solar system and eventually leave the solar system entirely. Without those assists, the mission would not have been possible with the technology of the time. Gravity assists are still used today. The Parker Solar Probe, which is studying the Sun, uses repeated gravity assists from Venus to gradually lower its orbit, bringing it closer and closer to the Sun. Each pass brings the probe a little nearer to its target, using the planet's gravity as a brake. Even in orbit, gravity is crucial. The International Space Station orbits the Earth at about 400 kilometers altitude. At that height, there is still gravity, about 90% as strong as on the Earth's surface. So why do astronauts float? Because they are in free fall. The station and everything in it are constantly falling toward the Earth, but they are also moving sideways fast enough that they keep missing the Earth. This is what an orbit is, falling around a planet. Astronauts experience what we call microgravity. They are still in the Earth's gravitational field, but they are in free fall, so they feel weightless. This weightlessness allows for all sorts of fascinating science. Flames behave differently in microgravity. Fluids form perfect spheres. Crystals grow in ways they cannot on Earth. Microgravity experiments have led to advances in materials science, medicine, and physics. But microgravity also poses challenges. As mentioned earlier, the human body does not do well in long-term weightlessness. Astronauts must exercise for hours each day to maintain muscle and bone density. Researchers are studying these effects to prepare for future missions to Mars, which would require astronauts to spend months in space. Gravity also determines where we can go in the solar system. Landing on the Moon is relatively easy because the Moon's gravity is weak. Landing on Mars is more challenging because Mars has a thin atmosphere and moderate gravity. Landing on a gas giant like Jupiter is essentially impossible because there is no solid surface to land on, and the gravity is crushingly strong. Some moons and asteroids have such weak gravity that landing is more like docking. The Japanese spacecraft Hayabusa 2 touched down on the asteroid Ryugu, collected a sample, and then lifted off again, all with minimal fuel. On a larger body, this would require a powerful rocket. But on an asteroid, where gravity is negligible, a gentle push is enough. In the future, we might build space elevators, structures that stretch from the Earth's surface into space. A space elevator would allow us to send cargo and people into orbit without rockets. The key technology is a cable strong enough to support its own weight against gravity. Materials like carbon nanotubes might make this possible someday. If we can build a space elevator, it will revolutionize access to space, making it far cheaper and easier to leave the Earth. Gravity, then, is both an obstacle and a tool. It holds us to the Earth, but it also governs the motion of everything in space. Understanding gravity is essential for exploring the cosmos. Now, let us return to the theme of mystery. We have talked about dark matter and dark energy, about quantum gravity, about the origin of the universe. But there are other mysteries too, smaller perhaps, but no less intriguing. One mystery is the orbit of Mercury. For centuries, astronomers observed that Mercury's orbit did not quite match Newton's predictions. The planet's closest approach to the Sun, called the perihelion, slowly shifted over time. Newton's gravity could explain most of this shift, but not all of it. There was a tiny discrepancy, just 43 arcseconds per century. Some astronomers proposed that there might be another planet, closer to the Sun than Mercury, whose gravity was causing the discrepancy. They even gave this hypothetical planet a name, Vulcan. But searches for Vulcan found nothing. The mystery was solved by Einstein. General Relativity predicted exactly the observed shift in Mercury's perihelion. The extra shift was caused by the curvature of spacetime near the Sun. Newton's gravity was not wrong, but it was incomplete. General Relativity gave a more accurate picture. This was one of the first triumphs of Einstein's theory. It explained something that Newton's gravity could not, and it showed that gravity, even in our own solar system, holds surprises. Another mystery involves the expansion of the universe. We know the universe is expanding, and that expansion is accelerating. But how fast is it expanding? Astronomers measure the expansion rate using a number called the Hubble constant. Here is the problem. Different methods of measuring the Hubble constant give different answers. Measurements based on the cosmic microwave background, the ancient light from the early universe, give one value. Measurements based on observations of nearby supernova give a slightly different value. The discrepancy is small, but it is persistent, and it might indicate that something is wrong with our understanding of the universe. This is called the Hubble tension. It might be a sign that dark energy is more complicated than we thought, or it might mean that the universe is not quite as uniform as we assumed. Or it could be an indication of new physics, something beyond general relativity. Scientists are working hard to resolve this tension, and the answer could reshape our understanding of cosmology. There is also the mystery of the universe's missing antimatter. According to our theories, the Big Bang should have created equal amounts of matter and antimatter, but our universe is made almost entirely of matter. Where did all the antimatter go? This is not directly a problem of gravity, but it is related. The early universe was governed by gravity and the other fundamental forces. Understanding why matter won out over antimatter might require us to understand how all the forces work together in those first moments after the Big Bang. And that brings us back to the quest for a unified theory, a theory that can describe gravity and quantum mechanics together. Gravity, it seems, is intertwined with every deep mystery in physics. It touches everything. And in trying to understand it, we are led into questions about the nature of matter, energy, space, time, and existence itself. As we have explored gravity, we have seen that it is far more than a simple force pulling things down. It is the architecture of the universe. It is the reason stars shine, planets orbit, galaxies form. It is the invisible hand that shapes everything from the smallest pebble to the largest supercluster. And it is still mysterious. We have come so far, from Newton's apple, to Einstein's spacetime, to the detection of gravitational waves. But we still do not have all the answers. Dark matter and dark energy are still hidden. Quantum gravity is still out of reach. The universe still has secrets to reveal. But that is what makes the journey worthwhile. The pursuit of knowledge is not about having all the answers. It is about asking the right questions. It is about being curious, open, willing to be surprised. And gravity, in its quiet way, continues to surprise us. Every time we think we understand it, the universe shows us something new. A black hole that behaves in an unexpected way. A gravitational wave signal that reveals a new type of collision. A distant galaxy whose motion hints at hidden mass. Each discovery is a reminder that there is always more to learn. And so, we continue. We build better telescopes. We design more sensitive detectors. We develop new theories. And slowly, piece by piece, the picture becomes clearer. But it will never be complete. The universe is vast, and our understanding is limited. There will always be new questions, new mysteries, new frontiers. And that is a beautiful thing. It means the journey of discovery never ends. Gravity holds the universe together, but it also pulls us forward into the unknown, toward understanding. It is the force that binds stars and galaxies. And it is the force that binds us to the cosmos, reminding us that we are part of something far greater than ourselves. So as we close this exploration, let us hold on to that sense of wonder. Let us remember that the universe is full of mysteries, and that we are fortunate enough to be able to explore them. Let us appreciate the beauty of gravity in all its subtle complexity. We are made of stardust. We are held by gravity. We are part of the cosmic dance, moving through space-time, connected to everything that exists. And that is enough. But wait, there is still so much more to explore. Gravity has layers upon layers of meaning, implications that ripple through physics, astronomy, philosophy, and even our daily experience. Let us continue this peaceful journey a bit longer. Think about how our understanding of gravity has evolved over the centuries. Before Newton, people had only vague ideas about why objects fell. Aristotle, the ancient Greek philosopher, thought that heavy objects fell because they wanted to return to their natural place. He believed the universe was divided into regions, and each element, earth, water, air, fire, had a place where it belonged. Heavy things fell down because down is where earth belonged. This idea persisted for nearly 2,000 years. It was not based on mathematics or careful measurement. It was philosophy, an attempt to make sense of the world through reasoning. And for most purposes, it worked well enough. People did not need precise predictions. They just needed to understand, in a general way, why things behaved as they did. But during the Renaissance, that began to change. Scientists started measuring things more carefully. They started doing experiments. Galileo Galilei, working in Italy in the late 1500s and early 1600s, conducted experiments with falling objects. He is said to have dropped objects from the Leaning Tower of Pisa to show that heavy and light objects fall at the same rate, though this story is probably more legend than fact. What Galileo really did was roll balls down inclined planes, carefully measuring their acceleration. He found that all objects, regardless of their weight, accelerate at the same rate when falling. This was revolutionary. It contradicted Aristotle and showed that gravity affects all objects equally. Galileo also studied the motion of projectiles. He showed that the path of a thrown object is a parabola, a curved shape that can be described mathematically. This was another step toward understanding gravity as a force that can be quantified and predicted. Then came Newton. Building on Galileo's work, Newton developed his laws of motion and his law of universal gravitation. He showed that the same force that causes an apple to fall also keeps the Moon in orbit. He gave humanity the first truly predictive theory of gravity, one that could be used to calculate the motion of planets with incredible accuracy. Newton's work transformed science. Before Newton, astronomy was largely descriptive. Astronomers could observe the planets and record their positions, but they could not explain why the planets moved as they did. After Newton, astronomy became predictive. You could calculate where a planet would be years or decades in the future. You could predict eclipses, the return of comets, the timing of tides. This was enormously powerful. It changed how people thought about the universe. The cosmos was no longer mysterious and unpredictable. It was a machine, governed by laws, and those laws could be known. But Newton's gravity had limits. It described gravity as a force that acted instantaneously across any distance. If the sun suddenly disappeared, Newton's gravity said the Earth would immediately fly off into space. But this raised a question. How could the sun's gravity reach across 93 million miles of empty space instantly? What was carrying the force? Newton himself was troubled by this. He wrote that the idea of action at a distance was absurd, but he did not have an alternative. He simply described how gravity worked without claiming to know why. For more than 200 years, scientists used Newton's gravity successfully. It worked for almost everything. But there were tiny discrepancies, small observations that did not quite fit. The orbit of Mercury was one. The bending of starlight near the sun was another. And then there was the question of how gravity worked at the fundamental level. Einstein's General Relativity resolved these issues. It eliminated action at a distance by describing gravity as the curvature of spacetime. Changes in the gravitational field do not happen instantaneously. They propagate at the speed of light, as ripples in spacetime. If the sun disappeared, it would take about 8 minutes for the Earth to feel the change, the same amount of time it takes light to travel from the sun to the Earth. General Relativity also explained the tiny wobble in Mercury's orbit and predicted the bending of starlight. And it opened up entirely new ways of thinking about the universe. It predicted black holes, gravitational waves, the expansion of the universe. It turned gravity from a force into geometry, from something that happens in space into something that is space. And yet, even general relativity is not the final word. It does not account for quantum mechanics. It cannot describe what happens at the center of a black hole or in the first instant after the Big Bang. There are still mysteries to solve. This is the story of gravity. It is a story of progress, of deeper and deeper understanding, but it is also a story of humility. Each time we think we have the answer, we discover new questions. Each theory, as powerful as it is, has limits. Now, let us think more deeply about gravitational waves. We touched on them earlier, but they deserve more attention. Gravitational waves are one of the most extraordinary predictions of general relativity, and their discovery has opened an entirely new way of observing the universe. Imagine space-time as a fabric. When massive objects accelerate, they create ripples in that fabric. These ripples spread outward at the speed of light, stretching and squeezing space itself as they pass. This is a gravitational wave. The effect is incredibly tiny. When a gravitational wave passes through the Earth, it might change the distance between 2 points by less than 1/1000th of the diameter of a proton. Detecting such a small change is extraordinarily difficult. That is why it took 100 years to detect gravitational waves after Einstein predicted them. The technology simply did not exist. But in the late 20th century, scientists began building detectors called interferometers. These devices use lasers to measure distances with incredible precision. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of two facilities, one in Louisiana and one in Washington State. Each facility has two long arms, each 4 kilometers long, arranged in an L shape. Lasers bounce back and forth along the arms, and the detectors measure the time it takes for the light to travel. If a gravitational wave passes through, it will stretch one arm and squeeze the other, changing the travel time of the light by a tiny amount. On September 14, 2015, LIGO detected a gravitational wave for the first time. The signal came from two black holes, each about 30 times more massive than the Sun, spiraling together and merging into a single black hole. The event happened more than 1 billion light-years away, and yet the ripples from that collision reached Earth, and LIGO detected them. The signal lasted only a fraction of a second, but in that brief moment, scientists could tell what had happened. They could measure the masses of the black holes. They could determine how far away the event occurred. They could even estimate the spin of the final black hole. This was a triumph. It confirmed one of the last major predictions of general relativity, and it demonstrated that gravitational wave astronomy is possible. Since that first detection, LIGO and other detectors, including Virgo in Italy and Kagura in Japan, have detected dozens of gravitational wave events. Most are black hole mergers, but some are neutron star mergers, which are even more fascinating. In 2017, LIGO and Virgo detected gravitational waves from two neutron stars colliding. This event was special because, unlike black hole mergers, neutron star mergers produce light. When the gravitational wave signal was detected, astronomers around the world pointed their telescopes at the source. They saw a burst of gamma rays, the most energetic form of light. They saw optical light, X-rays, radio waves. For the first time, humanity observed a single cosmic event with both gravitational waves and electromagnetic radiation. This was the beginning of multi-messenger astronomy. By combining information from gravitational waves and light, astronomers can learn far more than they could from either source alone. For example, the neutron star merger produced heavy elements like gold and platinum. The light from the event showed the signature of these elements, confirming that neutron star collisions are one of the primary sources of heavy elements in the universe. Gravitational waves also let us test general relativity in extreme conditions. When two black holes merge, the gravitational fields are incredibly strong, and spacetime is warped to an extraordinary degree. The fact that the observed signals match the predictions of general relativity so well is a powerful confirmation that Einstein's theory is correct, even in these extreme environments. But gravitational wave astronomy is still in its infancy. The current detectors are sensitive to relatively nearby events. Future detectors, like the planned Laser Interferometer Space Antenna, LISA, will be able to detect waves from much farther away and from different sources. LISA will consist of 3 spacecraft flying in formation, forming a triangle with sides millions of kilometers long. ITACOM will detect gravitational waves from supermassive black hole mergers, from binary star systems in our galaxy, and perhaps from exotic sources we have not yet imagined. With LISA and other future detectors, we will be able to observe the universe in ways that were impossible just a few years ago. We will hear the gravitational symphony of the cosmos, the hum of countless mergers, collisions, and cataclysms echoing across space and time. And gravitational waves might reveal entirely new physics. Some theories predict that there could be exotic objects, like cosmic strings or primordial black holes from the early universe, that would produce unique gravitational wave signatures. Detecting these would be a major discovery, opening up new areas of research. Now, let us think about orbits. We have mentioned orbits several times, but what exactly is an orbit, and why do objects orbit? An orbit is a balance between two things. First, there is gravity, pulling an object toward the center of mass. Second, there is the object's motion, its velocity, which carries it forward. If the object is moving fast enough sideways, it will keep missing the center of mass, falling around it rather than into it. That is an orbit. The moon orbits the Earth because it is moving sideways fast enough that, even as it falls toward the Earth, it keeps missing. The Earth orbits the Sun for the same reason, and the Sun orbits the center of the Milky Way galaxy. Orbits can take different shapes. The simplest orbit is a circle, where the object maintains a constant distance from the center of mass. But most orbits are ellipses, elongated circles with two focal points. In a planetary orbit, the Sun is at one focal point, and the planet moves along the ellipse, sometimes closer to the Sun, sometimes farther away. Johannes Kepler, working in the early 1600s, discovered the mathematical laws that describe planetary orbits. He found that planets move in ellipses, that they sweep out equal areas in equal times, and that there is a precise relationship between the size of an orbit and the time it takes to complete. These are Kepler's laws, and they were a major step toward understanding gravity. Newton later showed that Kepler's laws are a consequence of his law of universal gravitation. If gravity follows an inverse square law, meaning the force decreases with the square of the distance, then orbits must be ellipses. This was a beautiful unification. Kepler's empirical observations and Newton's theoretical framework fit together perfectly. Orbits are stable, but they are not unchanging. Over time, gravitational interactions with other objects can alter an orbit. The Moon's orbit around the Earth is slowly changing because of tidal forces. The planets in the solar system subtly influence each other's orbits. These effects are small, but over millions of years, they can be significant. There are also unstable orbits. If an object's orbit brings it too close to another massive object, the gravitational interaction can fling it out of the system entirely. This is how some comets and asteroids are ejected from the solar system. It is also how planets can migrate, moving inward or outward over time. Understanding orbits is crucial for space exploration. To send a spacecraft to another planet, engineers must calculate a trajectory that uses the least fuel. This often involves waiting for a specific alignment of the planets, called a launch window, and using gravity assist to gain speed. The journey to Mars, for example, typically takes about 7 months. The spacecraft follows an elliptical orbit around the Sun, starting at Earth and ending at Mars. The timing has to be just right, so that Mars is in the right place when the spacecraft arrives. This alignment happens about every 26 months, which is why Mars missions tend to launch in clusters during those windows. Orbits also determine where we can place satellites. Satellites in low Earth orbit, a few hundred kilometers up, take about 90 minutes to orbit the planet. They move quickly across the sky and can observe any point on Earth's surface as the planet rotates beneath them. Satellites in geostationary orbit, about 36,000 kilometers up, take exactly 24 hours to orbit. They stay above the same point on the equator, moving with the Earth's rotation. This makes them ideal for communications and weather monitoring. There are also polar orbits, which pass over the poles. allowing satellites to observe the entire surface of the Earth over time. And there are highly elliptical orbits, which bring a satellite close to the Earth for part of its orbit and far away for the rest. Each type of orbit has its uses, and choosing the right orbit is essential for a satellite's mission. Gravity governs all of this. Every satellite, every spacecraft, every object in space is subject to the same laws. And by understanding those laws, we can navigate the solar system, explore distant worlds, and use space for the benefit of humanity. Now let us think about the formation of the universe itself. The Big Bang is the prevailing theory for how the universe began, and gravity played a central role. In the beginning, about 13.8 billion years ago, the universe was unimaginably hot and dense. All of space, all of matter, all of energy was compressed into a single point, or perhaps a region smaller than an atom. Then, in an instant, the universe began expanding. In the first moments, the universe was filled with a hot soup of particles, quarks and gluons, and electrons, all moving at incredible speeds. As the universe expanded, it cooled. Within the first few minutes, quarks combined to form protons and neutrons. After about 3 minutes, protons and neutrons combined to form the first atomic nuclei, hydrogen and helium, and a tiny bit of lithium. But the universe was still too hot for atoms to form. Electrons could not attach to nuclei because they were constantly being knocked off by high-energy photons. The universe was opaque, filled with a glowing fog of particles and light. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to attach to nuclei. Atoms formed. The fog cleared. Light could travel freely through space for the first time. This light is still traveling today, stretched by the expansion of the universe into microwave radiation. We call it the cosmic microwave background, and it is one of the strongest pieces of evidence for the Big Bang. After atoms formed, gravity took over. The universe was not perfectly uniform. There were tiny variations in density, small regions where there was slightly more matter than average. Gravity pulled on these regions, attracting more matter. Over millions of years, these small variations grew into clouds of gas, hundreds of light years across. Inside these clouds, gravity continued to work. The densest parts of the clouds collapsed, heating up as they contracted. Eventually, the cores became hot enough for nuclear fusion to begin. The first stars were born. These first stars were massive and short-lived. They burned through their fuel in just a few million years, then exploded as supernovae, scattering heavy elements into space. Those elements, forged in the hearts of stars, seeded the next generation of stars and, eventually, planets. Over billions of years, gravity continued to shape the universe. Stars formed into galaxies. Galaxies formed into clusters. Clusters formed into superclusters, and superclusters formed the cosmic web. All of this structure, all of this complexity, emerged from tiny variations in density in the early universe, amplified by the relentless pull of gravity. And at the center of almost every galaxy, a supermassive black hole formed. We do not fully understand how these black holes grew so large. Some might have formed from the collapse of massive gas clouds in the early universe. Others might have grown by swallowing gas and merging with other black holes over billions of years. But gravity was the driving force behind all of it. The story of the universe is in many ways the story of gravity. Gravity turned a nearly uniform sea of hydrogen and helium into the rich, complex cosmos we see today. It built stars, planets, galaxies, and us. But gravity also governs the future of the universe. As we mentioned earlier, dark energy is causing the expansion of the universe to accelerate. If this continues, galaxies will move farther and farther apart. Eventually, galaxies outside our local group will be so far away that their light will no longer reach us. The universe will become a lonelier place. In the distant future, stars will stop forming. All the gas in the universe will be used up or dispersed. Existing stars will burn out one by one. Black holes will dominate, slowly evaporating through a process called Hawking radiation. Eventually, even black holes will disappear, leaving a cold, empty universe filled with nothing but faint radiation. This is one possible fate, called the heat death of the universe. It is not a comforting thought, but it is, far in the future, trillions of years from now. For now, the universe is vibrant and full of life, or at least full of the potential for life. And that brings us to another profound question. What role does gravity play in the existence of life? Life as we know it requires a stable environment. Planets need to be the right distance from their stars to have liquid water. They need to be large enough to hold an atmosphere, but not so large that the gravity is crushing. They need to be protected from asteroids and comets, perhaps by a large planet like Jupiter that can deflect or capture those threats. All of this depends on gravity. Gravity determines the structure of planetary systems. It governs the motion of planets and moons. It shapes the evolution of stars, determining how long they shine and how much energy they produce. Earth is habitable because of gravity. Our planet is the right size, with enough gravity to hold an atmosphere, but not so much that the surface pressure is unbearable. The Moon, with its weaker gravity, lost its atmosphere long ago. Mars, also with weaker gravity, has only a thin atmosphere, and its water is mostly evaporated or frozen. Gravity also plays a role in the evolution of life. On Earth, organisms evolved in a gravitational field. Plants grow upward toward the light, and their roots grow downward into the soil. Animals have evolved muscles and bones to support their bodies against gravity. The human heart pumps blood against gravity to reach the brain. Would life have evolved differently in a different gravitational field? Almost certainly. On a planet with stronger gravity, animals might be shorter and more heavily built. On a planet with weaker gravity, they might be taller and more fragile. And in the weightlessness of space, life would face entirely different challenges. Some scientists think that life might exist in places we do not expect, places where gravity plays a different role. For example, moons like Europa and Enceladus have oceans beneath their icy surfaces, kept liquid by tidal heating from their parent planets. Those oceans might harbor life, organisms adapted to living in the dark, under kilometers of ice, in a gravitational field weaker than Earth's. If we ever discover life elsewhere in the universe, studying how it has adapted to different gravitational conditions will teach us a great deal about the nature of life itself. But life is fragile. Gravity, the same force that makes life possible, can also destroy it. A large asteroid or comet, pulled by gravity into a collision course with Earth, could cause mass extinction. This has happened before. 66 million years ago, an asteroid about 10 kilometers across struck the Earth, triggering events that led to the extinction of the dinosaurs. Today, astronomers watch for near-Earth objects, asteroids and comets that might pose a threat. If a dangerous object is detected, there are plans to deflect it, perhaps by ramming it with a spacecraft or using a nuclear explosion to change its trajectory. Gravity is the threat, but understanding gravity is also the key to defending against it. Gravity, then, is both creator and destroyer. It builds worlds and stars, and it tears them apart. It makes life possible, and it can end it. It is a force of order, pulling matter together, but also a force of chaos, powering collisions and explosions. This duality is at the heart of the universe. Creation and destruction, order and chaos are not opposites. They are partners, working together to shape reality. Gravity is the force that mediates this dance, bringing things together and tearing them apart in an endless cycle. Now, let us think about some of the more speculative ideas related to gravity. These are not proven, and some might never be, but they are fascinating to consider. One idea is the holographic principle. This principle suggests that all the information in a three-dimensional region of space can be encoded on a two-dimensional surface, like a hologram. Applied to the universe, this means that our three-dimensional reality might be a projection from a two-dimensional boundary. This sounds strange, but it has some theoretical support. In certain theories of quantum gravity, the holographic principle helps resolve paradoxes about black holes. It suggests that the information that falls into a black hole is not lost, but encoded on the event horizon. If the holographic principle is true, it means that spacetime, as we experience it, might not be fundamental. It might be an emergent property, something that arises from deeper, simpler principles. And if spacetime is emergent, then gravity is also emergent. Another speculative idea is the simulation hypothesis. This is the notion that our entire universe might be a computer simulation, created by some advanced civilization. In this view, the laws of physics, including gravity, would be the rules programmed into the simulation. This idea is popular in certain circles, but it is very difficult to test. If we are in a simulation, how would we know? Would there be glitches, errors in the code that we could detect? Some physicists have proposed looking for patterns in the cosmic microwave background or in the distribution of galaxies that might hint at underlying computational structures. But so far, there is no evidence. The simulation hypothesis raises profound questions about the nature of reality. If the universe is a simulation, what is the nature of the reality outside the simulation? And who or what created it? These questions might be unanswerable, but they are worth pondering. There is also the idea of white holes. A white hole is the time reverse of a black hole. Instead of matter and light falling in, a white hole would be a region where matter and light burst out. Nothing can enter a white hole, just as nothing can escape a black hole. White holes are solutions to the equations of general relativity, but it is not clear if they can actually exist. They would require very specific conditions, and they might be unstable, quickly transforming into black holes or disappearing entirely. No white holes have ever been observed, and many physicists think they are purely theoretical. But if white holes do exist, they would be extraordinary. Imagine a fountain of matter and energy pouring out into the universe from a region of space-time. It would be the ultimate source, a cosmic wellspring. Another idea involves wormholes, hypothetical tunnels through space-time that connect distant regions of the universe. If you could enter one end of a wormhole, you might emerge from the other end, far away, without having traveled through the space in between. Wormholes are also solutions to the equations of general relativity, but they come with problems. To keep a wormhole open, you would need exotic matter, matter with negative energy density. No such matter has ever been observed. Without it, a wormhole would collapse as soon as you try to use it. Even if wormholes could be stabilized, traversing one would be extremely dangerous. The tidal forces near a wormhole could be immense, tearing apart anything that tried to pass through. And there are questions about causality. If you could use a wormhole to travel faster than light, you might be able to go back in time, creating paradoxes. Despite these challenges, wormholes remain a fascinating concept. They appear in science fiction as a way to travel between stars, and they inspire real research into the nature of spacetime. These speculative ideas show the richness of gravity as a topic. It is not just about falling objects and orbiting planets. It is about the fundamental nature of reality, the structure of spacetime, the limits of what is possible. And gravity continues to inspire new ideas. Every year, physicists publish papers proposing new theories, new ways of thinking about gravity and its role in the universe. Some of these ideas will turn out to be wrong, but some might be right, or at least point the way toward deeper understanding. Now, let us take a step back and think about what gravity means for us as individuals, living our lives here on Earth. Gravity is the force that grounds us, literally and metaphorically. It holds us to the planet. It gives us a sense of place, a connection to the ground beneath our feet. Without gravity, we would float away, untethered, lost in space. But gravity also represents something more abstract. It is a force that brings things together. It is the invisible pull that draws objects to each other, that creates connections, that builds structure. In a sense, gravity is a metaphor for relationships, for the bonds that hold communities together, for the forces that shape our lives. We are all connected, not just by gravity, but by shared experiences, shared history, shared humanity. And just as gravity holds the universe together, these connections hold us together. There is comfort in this. We are not alone. We are part of a vast web of relationships, stretching from our families and friends to the wider world and beyond, to the cosmos itself. Gravity reminds us of our place in the universe. We are small, but we are part of something immense. We are temporary, but we are connected to structures that span billions of years. We are fragile, but we are made of the same stuff as stars. And gravity also reminds us of the importance of balance. Just as an orbit is a balance between falling and moving forward, life is a balance between opposing forces. Work and rest, stability and change, holding on and letting go. Gravity, in its quiet way, teaches us about the nature of existence. It is constant, reliable, always present. It does not judge. It does not discriminate. It simply is, a fundamental part of reality, shaping everything from the smallest atom to the largest galaxy. As we come to the end of this exploration, let us take a moment to appreciate gravity in all its mystery and beauty. It is the force we misunderstand, yes, but it is also the force that holds everything together. It is the architect of the cosmos, the sculptor of space-time, the invisible hand that guides the dance of stars and galaxies. And it is the force that holds you right now, gently but firmly, to the surface of this beautiful planet. It is the force that keeps the air around you, the water in the oceans, the ground beneath your feet. It is the reason you can stand, walk, live. Gravity is the silent partner in everything you do. It is always there, always working, never resting. And it connects you to the universe in ways you might not have thought about before. So as you drift off to sleep tonight, think about gravity. Think about how it curves space-time, how it bends light, how it pulls galaxies together across billions of light years. Think about the mysteries that remain, the dark matter and dark energy, the quest for quantum gravity, the origin of the universe. And think about how you are part of all of this. You are not separate from the cosmos. You are woven into its fabric. The same laws that govern the motion of planets govern the beating of your heart. The same force that holds galaxies together holds you to the earth. You are made of stardust, shaped by gravity, living in a universe that is far more mysterious and far more beautiful than we ever imagined. Rest easy. Let go of the questions for now. They will still be there tomorrow, waiting to be explored. For tonight, just be. Be a part of the universe. Be a note in the cosmic symphony. Be a thread in the fabric of space-time. Gravity holds you. The earth holds you. The universe holds you. And in that embrace, you are safe. Sleep well. Dream of stars and galaxies, of black holes and gravitational waves, of the mysteries that fill the cosmos. And know that you are part of it all, connected by gravity, held by the universe, woven into the grand tapestry of existence. But before you drift completely into sleep, let us explore just a bit more. There are still stories to tell, still wonders to contemplate, still mysteries that deserve our attention. Let us return to Einstein for a moment, not to his theories, but to the man himself. Albert Einstein was working as a patent clerk in Switzerland when he developed his theory of special relativity in 1905. He was 26 years old, unknown in the physics community, spending his days evaluating patent applications and his evenings thinking about light and motion. Special relativity was revolutionary. It showed that time and space are not absolute, that they depend on the motion of the observer. It revealed that mass and energy are equivalent, related by the famous equation E equals mc squared. But Einstein knew that special relativity was incomplete. It did not include gravity. For the next 10 years, Einstein struggled to incorporate gravity into his framework. It was not easy. He later called it the hardest intellectual work of his life. He filled notebook after notebook with calculations, trying different approaches, making mistakes, starting over. The breakthrough came when Einstein realized that gravity could be understood as curvature. Space-time is not flat. It is bent by mass and energy, and objects moving through curved space-time follow curved paths, which we perceive as the effects of gravity. This insight required entirely new mathematics. Einstein had to learn differential geometry, a branch of mathematics that describes curved spaces. With the help of his friend Marcel Grossmann, a mathematician, Einstein developed the equations of general relativity. The equations are beautiful but complex. They describe how matter and energy curve space-time, and how that curvature affects the motion of matter and energy. It is a loop, a feedback. Matter tells space-time how to curve. Space-time tells matter how to move. Einstein published his theory in November 1915. It was met with a mix of admiration and skepticism. The ideas were so radical, so different from Newton's gravity, that many physicists struggled to accept them. But the theory made predictions that could be tested. And when those predictions were confirmed one by one, the skepticism faded. Einstein became famous. He was celebrated as a genius, a man who had seen deeper into the nature of reality than anyone before him. But Einstein himself was humble. He often spoke of the beauty of the universe, the elegance of the laws of nature. He saw his work not as a personal achievement, but as a glimpse into the mind of God, as he put it, using the word God to mean the deep order underlying reality. Einstein spent the rest of his life searching for an even deeper theory, a unified field theory that would combine gravity with electromagnetism and the other forces. He never found it, but his quest inspired generations of physicists, and the search continues today. Einstein's story reminds us that progress in science is not always smooth. It is filled with false starts, dead ends, and moments of doubt. But it is also filled with moments of insight, of clarity, of beauty, and those moments make the struggle worthwhile. Now let us think about some of the modern experiments and observations that are advancing our understanding of gravity today. One exciting area is gravitational wave astronomy, which we have discussed. But there are also efforts to detect gravity at smaller scales, to see if there are deviations from Newton's or Einstein's predictions in laboratory experiments. For example, scientists have done experiments to test the inverse square law, the idea that gravity decreases with the square of the distance. At very small distances, less than a millimeter, it is difficult to test this law because other forces, like electromagnetism, become much stronger than gravity. But some experiments have managed to probe these scales, looking for signs of extra dimensions or modifications to gravity. So far, no deviations have been found, but the search continues. There are also experiments to measure the gravitational constant, the number that describes the strength of gravity. This constant, usually denoted by G, is one of the fundamental constants of nature, but it is also one of the least precisely known. Different experiments give slightly different values, and scientists are working to improve the measurements and understand why there are discrepancies. Another area of research involves testing gravity in space. The European Space Agency's LISA Pathfinder mission tested technologies for detecting gravitational waves in space. It demonstrated that spacecraft can be isolated from disturbances well enough to detect the tiny signals of gravitational waves. This paves the way for LISA, the full-scale gravitational wave detector in space. There are also missions studying the effects of gravity on satellites. By precisely tracking the orbits of satellites, scientists can map the gravitational field of the Earth in incredible detail. This reveals variations in the Earth's density, from mountain ranges to underground water reservoirs. It also helps us understand processes like ice melt and sea level rise, which are crucial for understanding climate change. And then there are experiments testing the equivalence principle, one of the fundamental principles of general relativity. The equivalence principle states that all objects fall at the same rate in a gravitational field, regardless of their composition. Galileo tested this principle centuries ago, and it has been tested many times since. But modern experiments are far more precise. The microscope mission, launched by the French Space Agency, tested the equivalence principle to 1 part in 10 to the 15th power. That means it checked whether two objects of different composition fall at the same rate to within 1 part in 1,000 trillion. The result? They do. The equivalence principle holds, at least to the limits of the experiment. Why is this important? Because the equivalence principle is the foundation of general relativity. If it were violated even slightly, it would suggest that there is new physics beyond Einstein's theory. So far, the principle has passed every test. But physicists keep testing, because finding a violation would be a major discovery. There are also theoretical efforts to understand gravity in new ways. Some physicists are exploring the idea of entropic gravity, the notion that gravity is not a fundamental force, but an emergent phenomenon, arising from the statistical behavior of microscopic degrees of freedom. This is similar to how temperature is not a fundamental property, but emerges from the motion of atoms. If gravity is entropic, it would have profound implications for our understanding of spacetime and thermodynamics. It might also provide a new path toward understanding dark matter and dark energy. Other physicists are studying the connections between gravity and quantum information. They have found that certain properties of black holes, like entropy, are related to the amount of information encoded on the event horizon. This has led to insights about the holographic principle and the nature of spacetime. These are cutting-edge ideas, and they are still being developed, but they show that gravity continues to be a source of inspiration and discovery. Now, let us think about the role of gravity in shaping the structure of galaxies. We have talked about dark matter and how it provides the gravitational scaffolding for galaxies to form. But the details are fascinating. Galaxies come in many shapes. Some are spirals, with elegant arms curving out from a central bulge. Some are ellipticals, smooth and featureless, shaped like footballs or spheres. Some are irregulars with no clear structure. Why do galaxies have these different shapes? Gravity is part of the answer. When galaxies form, they start as clouds of gas collapsing under their own gravity. If the cloud is rotating, it flattens into a disk. Stars form in the disk, and over time, the disk develops spiral arms, created by density waves that move through the gas and stars. But not all galaxies form this way. Some form through mergers. When two or more galaxies collide, during a merger, the orderly structure of the original galaxies is disrupted. Stars are flung into new orbits. Gas is heated and compressed, triggering bursts of star formation. The result is often an elliptical galaxy, a system without the organized structure of a spiral. The Milky Way itself is a spiral galaxy, and it has undergone mergers in the past. It is also on a collision course with the Andromeda Galaxy. In about 4 billion years, the two galaxies will begin to merge. The process will take millions of years, and the result will be a larger, probably elliptical galaxy. During the merger, the solar system will likely be flung into a different part of the galaxy, but the sun and planets will almost certainly remain intact. The distances between stars are so vast that direct collisions are incredibly rare, but the gravitational interactions will be dramatic, reshaping the entire galaxy. Supermassive black holes also play a role in shaping galaxies. As gas falls into the black hole, it heats up and emits radiation. This radiation can push on the surrounding gas, driving it out of the galaxy or preventing it from cooling and forming stars. This process, called feedback, regulates the growth of galaxies. Without it, galaxies would form stars much more rapidly and would look very different from what we observe. The interplay between gravity, gas, stars, and black holes is complex. Astronomers use computer simulations to model these processes, trying to understand how galaxies evolve over billions of years. These simulations are incredibly detailed, tracking millions or even billions of particles, each representing a chunk of gas or a group of stars. The results are stunning. Simulations can reproduce the observed properties of galaxies, from their shapes to their sizes to the distribution of stars and gas. They show how gravity, acting over cosmic time, sculpts the universe, and they reveal something profound. The universe is not static, it is dynamic, ever-changing. Galaxies form, merge, evolve. Stars are born and die. Black holes grow and merge. And through it all, gravity is the driving force, pulling matter together, building structure, creating the cosmos we see. Now let us think about one of the most tantalizing questions in all of science. Are we alone in the universe? Gravity plays a central role in this question. The existence of life depends on the existence of planets, and planets are formed by gravity. The stability of planetary systems is maintained by gravity. The conditions that make a planet habitable are determined, in part, by gravity. For many years, we did not know if other stars had planets, but starting in the 1990s, astronomers began discovering exoplanets, planets orbiting other stars. the discoveries came quickly. Within a few years, dozens of exoplanets were known. Today, thousands have been confirmed, and there are likely billions in our galaxy alone. Most exoplanets were discovered using the transit method or the radial velocity method, both of which rely on the effects of gravity. The transit method detects the dimming of a star's light when a planet passes in front of it. The radial velocity method detects the wobble of a star caused by the gravitational pull of an orbiting planet. The discovery of exoplanets has transformed our understanding of planetary systems. We now know that planets are common, that they come in a wide variety of sizes and compositions, and that many stars have multiple planets. Some exoplanets are in the habitable zone, the region around a star where liquid water could exist on the surface. These planets are prime candidates in the search for life. If life exists elsewhere in the universe, it might be on one of these worlds. But finding life is not easy. Even if a planet is in the habitable zone, it might not be hospitable. It needs an atmosphere, a stable climate, protection from radiation. And even if all those conditions are met, life might not arise. We do not fully understand how life begins or how common it is. Still, the search continues. Astronomers are using telescopes to study the atmospheres of exoplanets, looking for signs of oxygen, methane, or other gases that might indicate life. Future missions, like the James Webb Space Telescope, will have the capability to probe these atmospheres in more detail. And there is always the possibility of finding signs of intelligent life, signals sent intentionally or unintentionally from distant civilizations. The search for extraterrestrial intelligence, SETI, scans the sky for radio signals that might be of artificial origin. So far, no such signals have been found, but the search continues, and the discovery of even one signal would be one of the most profound moments in human history. Gravity brought the planets into existence. It shaped their orbits, their climates, their potential for life. And if we ever discover life beyond Earth, it will be a testament to the creative power of gravity, to its role in building worlds and creating the conditions for life to flourish. Now, let us reflect on the journey we have taken tonight. We started with Newton's apple, a simple observation that led to a universal law. We moved to Einstein's spacetime, a radical reimagining of reality. We explored black holes, gravitational waves, dark matter, and dark energy. We ventured into the realms of quantum gravity, the Big Bang, the future of the universe. Along the way, we have seen that gravity is far more than a force pulling objects down. It is the fabric of space-time. It is the architect of the cosmos. It is the sculptor of galaxies, the creator of stars, the force that makes life possible. And we have seen that gravity is deeply mysterious. For all our progress, there is still so much we do not know. Dark matter and dark energy remain hidden. Quantum gravity is still out of reach. The ultimate fate of the universe is uncertain. But these mysteries are not failures. They are invitations. They are reminders that the universe is vast and complex, that there is always more to learn, always more to discover, and they are what make the journey so compelling. Science is not about having all the answers. It is about asking the right questions. It is about being curious, open, willing to be surprised. And it is about appreciating the beauty of the universe, even when we do not fully understand it. Gravity, in its quiet way, teaches us all of this. It is constant, reliable, always present. It does not demand attention. It simply is a fundamental part of reality, shaping everything from the smallest atom to the largest galaxy. And it connects us all. We are all subject to gravity. We all live in curved space-time. We are all part of the cosmic dance, moving through the universe, connected to everything that exists. This connection is profound. It means that we are not separate from the cosmos. We are part of it. The atoms in our bodies were forged in stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it came from the universe. We are made of stardust, held together by gravity, living on a planet that orbits a star in a galaxy that is one of billions. And in studying gravity, we are not just learning about the universe, we are learning about ourselves. We are discovering our place in the grand story of space and time. We are finding meaning in the vastness, connection in the isolation, beauty in the mystery. So as you drift off tonight, hold on to this sense of wonder. Let the questions linger. Let the mysteries remain. They are part of what makes the universe so beautiful. Tomorrow, the search will continue. New telescopes will peer deeper into space. New detectors will listen for gravitational waves. New theories will be proposed and tested. And slowly, piece by piece, we will uncover more of the truth. But tonight, just be. Be a part of the universe. Be a part of the gravitational dance. Feel the pull of the earth beneath you, the curve of space-time around you, the invisible threads connecting you to everything that is. You are not alone. You are part of something immense, something ancient, something beautiful. You are woven into the fabric of the cosmos, held by gravity, carried through space and time. And in that embrace you are safe. You are home. You are part of the eternal dance of stars and galaxies, of matter and energy, of space and time. Gravity is the force we misunderstand, but it is also the force that holds everything together. It is the rhythm of the cosmos, the heartbeat of the universe, the silent music that plays in the background of existence. And as you close your eyes and let sleep come, remember this: you are made of stardust. You are shaped by gravity. You are living in a universe that is far more mysterious and far more beautiful than we ever imagined. The same laws that govern the motion of galaxies govern the beating of your heart. The same force that bends space-time around a black hole curves gently around you. You are part of the cosmic dance, a note in the symphony, a thread in the fabric. And that is enough. You do not need to understand every detail to appreciate the beauty. You do not need to solve every mystery to feel the wonder. The universe is here. You are here. And gravity, in all its strange and subtle glory, holds you together. Rest easy. Let go of the day. Let go of the questions. They will still be there tomorrow, waiting to be explored. But for now, just rest. Dream of stars and galaxies, of black holes and gravitational waves, of the cosmic web stretching across billions of light years. Dream of the mysteries that fill the universe, of the dark matter holding galaxies together, of the dark energy pushing the universe apart. And know that you are part of it all. You are connected by gravity, held by the universe, woven into the grand tapestry of existence. You are a child of the cosmos, made of the same stuff as stars, living on a planet that is hurtling through space at incredible speed, yet feeling perfectly still because you are moving with it. Gravity grounds you, it holds you. It connects you to the earth, to the sun, to the galaxy, to the universe. And in that connection, there is peace. There is belonging. There is home. Sleep well. Let the universe hold you in its embrace. Let gravity do its quiet work, keeping you safe, keeping you grounded, keeping you connected to everything that is. And may your dreams be filled with wonder. May you see the beauty of the cosmos in your mind's eye. May you feel the connection to the stars, to the galaxies, to the vast and ancient universe that surrounds us all. Good night. Rest peacefully, and know that gravity, the force we misunderstand, the force that shapes the universe, is also the force that holds you gently as you sleep, connecting you to the cosmos, making you part of the eternal dance. You are stardust. You are held by gravity. You are part of the universe. And in that knowledge, there is comfort, there is wonder, there is peace. But let us linger just a bit longer in this exploration. There are still more layers to uncover, still more connections to make, still more beauty to appreciate in the phenomenon we call gravity. Think about how gravity operates at different scales. At the smallest scale, the quantum scale, gravity is almost imperceptible. Two electrons sitting side by side exert a gravitational attraction on each other, but that attraction is so weak compared to the electromagnetic force between them that it can be ignored. The electromagnetic force is about 10 to the 40th power stronger than gravity at this scale. That is a 1 followed by 40 zeros. Gravity is utterly dwarfed. Yet at the larger scales, gravity dominates. It is the only force that matters when we talk about the motion of planets, stars, and galaxies. Why is there this dramatic shift? Because gravity has a special property. It is always attractive. It never repels. Electromagnetic forces can be attractive or repulsive. Positive charges repel each other. Negative charges repel each other. Only opposite charges attract. This means that large objects, which contain equal numbers of positive and negative charges, are electrically neutral. The attractive and repulsive forces cancel out. But gravity does not work this way. There is no negative mass, no anti-gravity. Every particle of matter attracts every other particle. And so, when you put together a large object, all those tiny gravitational attractions add up. The more mass you have, the stronger the gravitational pull. This is why gravity dominates at large scales. A planet has so much mass that its gravitational pull is immense, even though the gravitational attraction between any two atoms in the planet is negligible. The cumulative effect is what matters. This also explains why we can feel gravity so easily, even though it is the weakest of the fundamental forces. The Earth has enormous mass, and all of that mass is pulling on you. The electromagnetic forces from all the atoms in the Earth cancel out, but the gravitational forces add up. Now, let us think about a related question. Why is gravity so weak? This is one of the great mysteries of physics, sometimes called the hierarchy problem. The weakness of gravity has profound implications. It means that, on the scale of atoms and particles, gravity is irrelevant. Quantum mechanics can ignore gravity and still make incredibly accurate predictions. But it also means that, to study gravity directly, you need enormous masses. You cannot do gravitational experiments with single particles. Some theories suggest that gravity is weak because it is diluted across extra dimensions. If there are hidden dimensions that we cannot see, and if gravity can spread into those dimensions while the other forces cannot, then gravity in our three-dimensional space would appear weaker. This idea is part of string theory and related theories. It is speculative, but it offers a possible explanation for why gravity is so different from the other forces. Another mystery is the nature of spacetime itself. We have talked about spacetime as if it is a real, physical thing, a fabric that can be bent and stretched. But is it? Or is spacetime just a mathematical tool, a convenient way of describing relationships between events? This is a deep philosophical question. Some physicists think spacetime is fundamental, a real entity that exists independently of the matter and energy it contains. Others think spacetime is emergent, something that arises from more basic entities, like quantum bits of information or networks of connections. If spacetime is emergent, then the question becomes, what is it emerging from? What is the more fundamental reality? These are questions at the cutting edge of theoretical physics, and there are no clear answers yet. But the very fact that we can ask these questions shows how far we have come. A few centuries ago, gravity was a mysterious force. Today, we can debate whether the space-time it curves is even real. We have gone from ignorance to deep, sophisticated uncertainty, and that is progress. Let us also think about the role of symmetry in gravity. Symmetry is a powerful concept in physics. When a system has symmetry, it means that certain transformations leave the system unchanged. For example, a perfect sphere has rotational symmetry. You can rotate it by any angle, and it looks the same. General relativity has a profound symmetry called general covariance. This means that the laws of physics are the same in all coordinate systems. You can describe spacetime using any coordinates you like, and the equations of general relativity will have the same form. This is not just a mathematical convenience. It is a deep principle reflecting the fact that spacetime itself is what matters, not any particular way of labeling points in spacetime. This symmetry is related to the equivalence principle, the fact that all objects fall at the same rate, regardless of their composition, is a consequence of the symmetry of spacetime. It is a beautiful connection between a simple observation and a deep mathematical structure. Symmetries also play a role in quantum field theory, the framework that describes the other fundamental forces. Different forces are associated with different symmetries. For example, the electromagnetic force is associated with a symmetry called gauge symmetry. The strong nuclear force has its own gauge symmetry. One of the goals of theoretical physics is to find a symmetry that unifies all the forces, including gravity. If such a symmetry exists, it would suggest that all the forces are different aspects of a single, more fundamental force. This is the dream of a unified field theory, the quest that Einstein pursued for the last decades of his life. We have not found that symmetry yet, but the search continues, driven by the belief that the universe, at its deepest level, is simple and elegant. Now, let us turn our attention to the concept of spacetime, curvature in more detail. We have said that mass curves spacetime, and that this curvature is what we perceive as gravity. But what does this curvature actually look like? Imagine a trampoline. If you place a heavy ball in the center, the trampoline sags, creating a curved surface. If you then roll a smaller ball nearby, it will curve toward the heavy ball, following the shape of the trampoline. This is the rubber sheet analogy, and it is a useful way to visualize spacetime curvature. But the analogy has limits. A trampoline is a two-dimensional surface curving in three-dimensional space. Spacetime is four-dimensional, 3 dimensions of space and 1 of time, and it curves in ways that are difficult to visualize. Moreover, the trampoline analogy makes it look like there is something outside spacetime, some higher dimensional space in which spacetime curves. But general relativity does not require this. Spacetime can be intrinsically curved in on itself, without needing to be embedded in anything else. To understand this, think about the surface of the Earth. The surface is curved, but it does not curve into anything. It is a two-dimensional surface that is intrinsically curved. You can walk around the Earth and return to your starting point without ever leaving the surface. The curvature is a property of the surface itself. Spacetime is similar. It is curved by the presence of mass and energy. But that curvature is an intrinsic property of spacetime. there is no need for a higher dimensional space. The mathematics of general relativity describes this curvature precisely. The curvature of spacetime at any point is determined by the distribution of mass and energy nearby, and the curvature, in turn, determines how objects move. It is a beautiful, self-consistent framework, but curvature can be complex. In some regions of spacetime, the curvature is gentle, like the curve of the Earth's surface. In other regions, near a black hole, the curvature is extreme, warping spacetime to such a degree that even light cannot escape. And in some solutions to the equations of general relativity, spacetime has exotic properties. It can have wormholes, shortcuts through spacetime. It can have closed time-like curves, paths that loop back on themselves, allowing for time travel. These solutions are mathematically valid, but it is not clear if they can exist in reality. They often require exotic matter with properties that we have never observed. Still, the fact that these solutions exist in the mathematics suggests that space-time is far stranger than our everyday experience would suggest. And it reminds us that we are still far from fully understanding the nature of space and time. Now, let us think about the observational evidence for general relativity. We have mentioned several tests, but there are many more. One of the most famous is the Pound-Rebka experiment, conducted in 1959. This experiment measured gravitational redshift, the effect that gravity has on the frequency of light. According to general relativity, light traveling upward in a gravitational field loses energy, and its frequency decreases, shifting toward the red end of the spectrum. Light traveling downward gains energy, and its frequency increases, shifting toward the blue. The experiment used a tower at Harvard University. Gamma rays were emitted from the bottom of the tower and detected at the top. The change in frequency was tiny, only a few parts in 1,000 trillion. But the experiment was precise enough to measure it, and the result matched the prediction of general relativity perfectly. Another test involves the Shapiro time delay. When light passes near a massive object like the Sun, the curvature of spacetime causes the light to take longer to reach its destination. This delay is tiny, only microseconds for light passing near the Sun. But it can be measured by sending radio signals to spacecraft on the far side of the Sun and timing the round trip. Such experiments have been done many times, and the results always agree with general relativity. The theory has passed every test. There are also tests involving the orbits of planets. Mercury's perihelion shift was the first, but modern measurements have confirmed similar effects for other planets and even for artificial satellites. The orbits of GPS satellites, for example, are affected by both general relativity and special relativity, and the GPS system must account for these effects to function correctly. And then there are gravitational waves. The detection of gravitational waves and the agreement between the observed signals and the predictions of general relativity is one of the strongest confirmations of the theory. Gravitational waves are a direct consequence of the dynamic nature of spacetime, and their existence was once doubted. Now, they are observed regularly, and they have become a tool for exploring the universe. All of this evidence points to the same conclusion. General relativity is correct, at least within the domains where it has been tested. It describes gravity accurately on scales from the solar system to the entire observable universe. But we also know that general relativity cannot be the final word. It does not include quantum mechanics. It cannot describe what happens at the center of a black hole or in the first instant after the Big Bang. There is still work to do. Now, let us think about the human side of gravity, How does our experience of gravity shape our lives and our perceptions? From the moment we are born, we are immersed in gravity. We learn to lift our heads, to sit up, to stand, to walk, all by learning to work with and against gravity. Our muscles develop strength to support our bodies. Our bones grow dense to bear the weight. Gravity gives us a sense of direction. Up and down are not arbitrary. They are defined by gravity. The sky is up, where we have to work against gravity to go. The ground is down, where gravity pulls us. This sense of direction is deeply ingrained. When astronauts first experience weightlessness, many report feeling disoriented. Without gravity to define up and down, the brain struggles to make sense of the environment. Some astronauts experience space sickness, a kind of motion sickness caused by the conflicting signals the brain is receiving. But after a few days, most astronauts adapt. The brain is flexible. It can learn to function without gravity's guidance. And many astronauts report that weightlessness is exhilarating, a freedom they have never experienced before. Gravity also affects our perception of weight and effort. When you lift a heavy object, you are working against gravity. The effort you feel is directly related to the strength of the gravitational pull. On the Moon, where gravity is weaker, the same object would feel lighter. You could lift it more easily, jump higher, move with less effort. This is why astronauts on the Moon could make those famous bounding leaps. They were still wearing heavy spacesuits, but the Moon's weaker gravity made it easier to move. Each step took them farther, and they seemed to float across the surface. Gravity also influences our sense of time, though not in a way we can feel directly. As we have discussed, time runs slower in stronger gravitational fields, but the difference is so small on Earth that we do not notice it. A clock at sea level runs slightly slower than a clock on a mountaintop, but the difference is measured in nanoseconds per day. Still, the fact that time is affected by gravity is profound. It means that time is not absolute. It is relative, dependent on the gravitational field and the motion of the observer. This is one of the most counterintuitive ideas in all of physics, but it is confirmed by countless experiments, and it has practical implications. GPS satellites orbit high above the Earth, where gravity is weaker and time runs faster. If the satellites did not correct for this effect, GPS positions would drift by several kilometers per day. The system works because engineers understand general relativity and program the corrections into the satellites. So, even if we do not feel the effects of gravitational time dilation directly, we rely on our understanding of it every day. Now, let us reflect on the vastness of the cosmos and our place within it. The universe is enormous, far larger than we can easily comprehend. The observable universe extends for about 93 billion light-years in all directions. That is the distance light has traveled since the Big Bang, taking into account the expansion of space. But the actual universe might be much larger, perhaps infinite. We can only see a finite region, limited by the speed of light and the age of the universe. Beyond that horizon, there might be more galaxies, more stars, more worlds. We will never see them, because their light has not had time to reach us. Within the observable universe, there are an estimated 2 trillion galaxies. Each galaxy contains billions or trillions of stars, and each star might have planets. The numbers are staggering, almost incomprehensible, and yet, we are part of this vast cosmos. We live on one small planet, orbiting one ordinary star, in one galaxy among trillions. It is easy to feel insignificant in the face of such vastness, but there is another way to look at it. We are the universe becoming aware of itself. We are made of atoms forged in stars, shaped by gravity, living on a planet that formed from the dust of ancient supernovae. We are not separate from the cosmos. We are a part of it, and we have the capacity to understand. We can look up at the night sky and wonder. We can ask questions about the nature of reality. We can build telescopes and detectors, write equations and theories, all in an effort to make sense of the universe. This is remarkable. In a cosmos that spans billions of light years, filled with countless stars and galaxies, there exists a species capable of contemplating its own existence, of studying the laws of nature, of feeling awe and wonder. Gravity connects us to this cosmos. It is the force that binds the Earth to the Sun to the galaxy to the universe. It is the invisible thread that ties everything together. And in studying gravity, we are not just learning about a force. We are learning about our place in the grand story of space and time. So as you prepare to sleep, hold on to this sense of connection. You are not alone. You are part of something immense, something ancient, something beautiful. The same force that shapes galaxies also holds you to the Earth. The same laws that govern the motion of stars also govern the beating of your heart. You are made of stardust. You are held by gravity. You are part of the cosmic dance. And in that dance, there is meaning, there is beauty, there is wonder. Let gravity do its work. Let it hold you, ground you, connect you. Feel the Earth beneath you, solid and steady. Feel the pull of the planet, gentle but constant, keeping you safe. And as you close your eyes, let your mind drift. Drift through the cosmos, past the moon, past the planets, past the sun. Drift through the Milky Way, past billions of stars, past clouds of gas and dust, past the supermassive black hole at the center. Drift beyond our galaxy, through the vastness of intergalactic space, past other galaxies, each one a vast city of stars. Drift through the cosmic web, the filaments and voids that stretch across the universe. And then drift back through the galaxies, back through the Milky Way, back to the solar system, back to Earth, back to your place on this beautiful planet, held by gravity, connected to the cosmos. You are here. You are part of the universe, and the universe is part of you. In your atoms, in your molecules, in the very structure of your body, you carry the history of the cosmos. You are a child of the stars, a product of billions of years of cosmic evolution. And gravity has been there every step of the way. Gravity formed the first stars. Gravity shaped the galaxies. Gravity brought together the dust that became the Earth. Gravity holds the atmosphere that you breathe. Gravity gives you weight, gives you direction, gives you a sense of place. Without gravity, none of this would exist. No stars, no planets, no galaxies, no Earth, no life, no you. Gravity is the force that makes everything possible. And so, as you rest, as you let sleep come, give thanks to gravity, not in a religious sense, but in a sense of appreciation. Appreciate the beauty of the universe, the elegance of the laws of nature, the wonder of existence. Gravity is the force we misunderstand, but it is also the force that holds everything together. It is the silent partner in everything we do, the invisible hand that guides the dance of the cosmos, the foundation upon which reality rests. And as you drift off to sleep, know that gravity is holding you. The Earth is holding you. The universe is holding you. You are safe. You are grounded. You are connected. Dream of the cosmos. Dream of stars being born and dying. Dream of galaxies spiraling through space. Dream of black holes, mysterious and powerful. Dream of gravitational waves, ripples in space-time. carrying news of distant events. And dream of yourself, a tiny part of this vast universe, yet precious, unique, connected to everything that is. You are stardust. You are held by gravity. You are part of the eternal dance. Rest now. Let go of the questions. Let go of the mysteries. They will still be there tomorrow. But for now, just rest. Just be. Be a part of the universe. Be a note in the cosmic symphony. Be a thread in the fabric of spacetime. Gravity is with you. The earth is with you. The universe is with you. And in that embrace you are home. Sleep well, sleep deeply. And may your dreams be filled with the beauty and wonder of the cosmos, with the mystery of gravity, with the joy of being alive in this extraordinary universe. Good night, sweet dreams, and may you wake tomorrow with a heart full of wonder and a mind eager to explore the mysteries that still await us in the cosmos and in ourselves. The universe is vast, the universe is beautiful, and you are a part of it. Always remember that. You are made of stardust, held by gravity, living in a cosmos that is far more mysterious and far more beautiful than we ever imagined. And that is a gift, a profound and precious gift. Rest now. Let gravity hold you. Let the earth cradle you. Let the universe embrace you. And sleep peacefully, knowing that you are exactly where you belong, connected to everything, part of the cosmic dance, held by the force we call gravity. And before you fully surrender to sleep, one last thought. Consider how remarkable it is that we, tiny beings on a small planet, can understand something as vast as gravity. We can write equations describing the motion of galaxies. We can predict the behavior of black holes. We can detect ripples in space-time itself. This understanding is not yet complete. There are still mysteries, still questions without answers. But the very fact that we can comprehend gravity at all is extraordinary. It suggests that the universe is knowable, its secrets can be unlocked. We have a place in things, and perhaps that is the most profound lesson of gravity. It teaches us humility, showing us how small we are. But it also teaches us empowerment, showing us what we can achieve. We are small, yes, but we are also capable of understanding the cosmos. We can grasp the invisible threads that connect everything. We can see the patterns, the beauty, the order underlying the apparent chaos. This is the gift of science, and specifically the gift of our understanding of gravity. It gives us a way to connect with the universe, to appreciate it, to marvel at it, and it reminds us that we are not separate from nature. We are part of it, subject to the same laws, made of the same stuff, dancing to the same cosmic rhythm. So rest now, with this knowledge in your heart. You are connected to everything. You are held by gravity, shaped by the universe, part of the eternal dance. And in that dance, there is peace, there is beauty, there is home. Sleep well, dear traveler through the cosmos. Until tomorrow, when we continue our journey through the mysteries of existence. Good night.